Nothing beats this video. What we're going to do is apply our new knowledge of implicit differentiation to come up with the power rule, but now for rational exponents. Let's go. Now look, this is the power rule that we've established thus far. Right here, recall, right? If you have an integer value of n, negative or positive whole number for n, including 0 as well, then we have already established that the derivative of a power function of the form x to the n with respect to x is n times x to the n minus 1. And that's that, right? We've established that. But that was only restricted to integer values of n. So we'd like to extend this rule now so that the powers also include rational values of n. So like I said earlier, we're going to apply implicit differentiation to extend this rule. So what we're going to do is we're going to let a and b be integers. So both of them could be positive or negative whole numbers, or 0, except b. b can't be 0 here, as we'll see why. And that is because we're going to consider the function y is f of x is x to the power of a divided by b. And so as you can see, we don't want b to be 0, because then that won't be defined. And then we're also going to assume that if b is even, then we only restrict the values of x to be non-negative. So we don't have to worry about taking square roots of negatives, basically, or fourth roots or sixth roots or whatever. So as you can see here, what we have is a function f of x, which is a power function exactly of concern in this video, and that is a power function to the power of a rational number. A divided by b is definitely rational, just meaning it's a ratio of two integers and it's defined. So think fractions that involve strictly whole numbers in the numerator and denominator, a and b, positive or negative that is, and b is non-zero. Now notice, if we have that equation there, our function y is equal to x to the power of a divided by b, then if I just simply raise each side to the power of b, which we know is non-zero, then the equivalent statement right here is y to the power of b is equal to x to the power of a. And a and b are integers, and we've already established the power rule for integer value exponents. And thus what we'd like to do is figure out what dy dx is by applying the process of implicit differentiation to the equivalent equation y to the b is equal to x to the a. So that's what we'll start with. Y to the b is equal to x to the a. Apply my differentiation step. Differentiate both sides of this equation with respect to x, since y is considered to be the output variable here and x the input variable. Now on the left hand side, keeping in mind what I just said, y is the dependent variable, then I got to apply chain rule right here, right? So I apply the power rule to y, the unknown function in this assumption, and hence b comes down, lower the power of y by 1, so b times y to the b minus 1, times the derivative of that inner function, dy dx, and on the right hand side we have x to the a, which is being differentiated with respect to x, so by power rule that's just a times x to the a minus 1. And now what we'll do is we'll start applying some algebra and whatnot, and we'll go through this step by step. So the first thing I did in this first step right down here is that I went ahead and just divided both sides of the equation by b times y to the b minus 1, so I isolated my dy dx. Now, when I did that, remember, go back up here real quick. We know that y is x to the power of a divided by b. And so down in this step where we were at, all I'm doing is replacing that y with x to the a divided by b. And now I'll start playing some games. So notice I just took this a divided by b, I threw it out in front. That's just a constant coefficient of this expression. And here, all I'm doing is using the power rule for exponents to rewrite x to the power of a divided by b, all of that to the power of b minus 1. Well, you multiply powers, right? So you get that result, x to the power of a times the quantity b minus 1, all divided by b. Then, by some simplification, I can write the next statement here. Keep your eyes closed down here. I'm going to make some room. This statement, which is just the result of taking a times b minus 1 over b and thinking of it as a over 1 times b minus 1 over b, and then simplifying this part right here, which of course this is just the same as 1 minus 1 over b. And so what do I get? I get x to the a minus a over b. And then this final step right here, what I did is I just said, well, look, I got x to the a minus 1 on top and x to the a minus a over b in the denominator. And therefore, I can subtract the denominator exponent from the numerator exponent to get x to the a minus 1 minus the a, and then plus the a over b, right, minus the minus. Notice in that expression, the a's cancel out. A minus a is 0. And so I can write the positive term a divided by b in front, minus that 1, giving us the result that dy dx for this situation is a divided by b times x to the a divided by b minus 1. And if you just think, okay, well, a divided by b is just a number, right? It is some rational number, a ratio of two integers. Call it n right down here. Then this statement that we just concluded is really just the same as saying that the derivative with respect to x of the power function x to the n, hence y is equal to x to the n, is n, which is a over b, times x to the n minus 1, or a divided by b minus 1 power. And thus, that's our rule. It checks out. And now we've established that the power rule also works when our powers are rational numbers. So that's nice, right? Because now we can do more things easily. Let's find a few derivatives before we wrap up this video here. Let's find the following derivatives. All right. First one, let's differentiate the function 5 divided by the square root of x with respect to x. So what we do is we notice that this is the same as saying derivative with respect to x of the function 5 times x to the negative 1/2 power. Now, of course, you can use the quotient rule here, but if you can avoid the quotient rule, things are more efficiently done, usually. Notice I have a situation, 5 times x to the negative 1/2, that's the function I'm differentiating. It's a power function with the power being a rational number. And so what can we do? Take the 5, multiply it with, of course, the derivative with respect to x of x to the negative 1/2 power. And now I apply the power rule to x to the negative 1/2 to get 5 times, bring down the power, negative 1/2 times x to the negative 1/2 minus 1 power, which is a negative 5/2 times x to the negative 3/2. Now, depending on the situation, you may want to rewrite this in radical form. And so that is something that just all depends on the situation. However, just to see it once, this is really the same as writing negative 5 over 2x to the positive 3/2 power, which is the same thing as saying negative 5 over 2 square root of x cubed, or otherwise known as negative 5 divided by 2 times x root x. So really these two things I'm boxing in here are equivalent, but just as like a kind reminder of how to convert your rational exponents into radical form. You could do it both ways. But probably the biggest takeaway, right, is the fact that we can now just use the power rule to differentiate functions that have rational powers on them. Here's another one. How about tangent of the cube root of t? Let's differentiate that with respect to t. Now, notice, before I apply my differentiation, I'll just write it as d dt of tangent of t to the 1/3 power. And so it's chain rule, as we can see, but the chain rule involves our new rule, this power rule for rational exponents. So, by the chain rule, it's the same as d dt of t to the 1/3, derivative of the inner function with respect to t, times, well, the derivative of the outer function tangent is a secant squared function, and leave the inner function alone. And now, once I differentiate my t to the 1/3 power, that becomes a 1/3 t to the negative 2/3 power, right? 1/3 minus 1 is negative 2/3, times secant squared of t to the 1/3, or if you prefer, secant squared of t to the 1/3 over 3t to the 2/3. And again, we could write that in radical form if we wanted to. But in the end, that's probably good enough. Even having the positive rational exponents isn't always necessary, but sometimes it's nice. All right, one last one, and then we're done. Here we go. Last function to differentiate. And what do we have here? We got the function e to the power of w to the power of 3/4. And of course, we're going to differentiate that with respect to w. So this is another chain rule situation. E to the power of a function, got to differentiate that. So chain rule says, take the derivative with respect to w, the input variable, of that function, that inner function, w to the 3/4 power, and then multiply it with the derivative of the outer function, e to the stuff, but the derivative of e to the stuff is just e to the stuff. So it's going to be e to the w to the 3/4 power. And now we apply our new extended, if you will, power rule, and we get derivative of w to the 3/4 with respect to w is 3/4 w to the negative 1/4, 3/4 minus 1, negative 1/4, times e to the w to the 3/4, or if you prefer, 3e to the w to the 3/4 power, all divided by 4w to the 1/4 power. And once again, you could turn that into an expression that has the radical notation in it, but I'll just leave as so. And so there you go. That is the video we just showed. Power rule is growing, and eventually we'll show that this is true for all real numbers. The power rule, that is. But we're not quite there. So we showed it was true in this situation. We did some examples, and there you go. That's the end of the video. So until the next video, math and beats, later.